Today's lesson is section 9-1, developing conditions for parallelograms, and we're going to specifically look at the area of a parallelogram. So looking at our objective for today, our first one is going to be to find the area of parallelograms, and then the second one is going to be to prove a quadrilateral is a parallelogram. Let's first look at the first objective, to find an area of a parallelogram. As you can see here, any side of a parallelogram can be called a base. So it doesn't matter, there's not one specific base for any parallelogram. For each base, there's a corresponding altitude. So here in parallelogram ABCD, I would say that segment AD is considered the base. And altitude can be any perpendicular segment between the parallel lines. So I'd say, here's my parallel line BC and AD, those are my parallel lines. So if AD is the base, then BX and CY are my altitudes. So let's take a look at this a little further. Right here, in this next example, I have if BC is the base. So this time BC is the top, then AW and segment BZ are my altitudes. So as you can start to pick up on, my altitudes go to the base. So they start at a vertice and they go to form a 90-degree angle at the base. So wherever your altitudes go, that helps you determine what the base of the parallelogram is. Here's another example. It's the same parallelogram, but this time I have CD as my base, because as I can tell, BM and AN are my altitudes. They form the 90-degree angle at the base, at segment CD. Therefore, here's my base, and once again, my altitudes. One last time. This time I would say that AB is my base. Again, I can tell that because DG and CH are my altitudes. I can tell their altitudes. They form a 90-degree angle at the side opposite from the vertex where they start. So moving on. Here we're going to get into what how to find the area of a parallelogram. We're going to call the length of the altitude, we're going to call that the height in the parallelogram. And that's going to lead us to the formula for finding the area of a parallelogram. So the area of a parallelogram is going to equal base times height. So that's where B is the length of the base and H is the height of the parallelogram. That's why it is so important that you recognize what both the base is and what the height is. So we're going to use this formula for our first few examples. This first one, I want to find the area. I have parallelogram ABCD. I want to find the area of this parallelogram. Here's our formula that we just had on the previous slide. Area equals base times height. So in this figure, I need to figure out what my base is and what my height is. Again, we said the height is the length of the altitude. I can see this right here. Starts at a vertex, forms a 90-degree angle at the side opposite. Starting at C going down to segment AD, this 4 meters must be my altitude or my height. Wherever the altitude heads, down here, so segment AD must be my base. So to find the area of this parallelogram, I'm going to take area equals base, 12, times height, 4. Area equals 48 meters squared. This is 12 meters times 4 meters. Meters times meters gives you meters squared. So the area of this parallelogram ABCD is 48 meters squared. Moving on. I first want to name the base of this parallelogram, and then I want to find the area. So see, this time on this parallelogram, I have multiple sides that are labeled. So I have segment BC is 60 feet. I have segment BA is 45 feet. And I have this right here. This looks to be my altitude. Again, it starts at a vertex, forms a 90-degree angle at the side opposite. So this segment is my altitude, therefore making AD my base. Although it's not labeled, I can tell that AD is going to be 60 feet. One of the properties of a parallelogram is something that proves something a parallelogram is it has opposite sides that are congruent. So if the top BC is the top BC is 60 feet, then the bottom AD has to be 60 feet as well. And once again, opposite sides of a parallelogram are congruent. So now that I know this is my base, I can figure out what the area of this parallelogram needs to be. So once again, using the formula from earlier, area equals base times height. Area is going to equal my base, 60 feet, times my height, 36 feet. You can all use calculators on this. Plug it into your calculator. You're going to find that the area of this parallelogram, 60 times 36, is going to be 2,160 feet squared. Moving on. This time I want to find the missing base or height of each parallelogram. Notice the big difference here. I'm giving you the area. The area of this parallelogram this time is 120 millimeters squared. Looking at the parallelogram, I have AD, and I have this segment right here. Starts at a vertex, forms a 90-degree angle, so this missing x is going to be the altitude, or the height. AD is going to be my base. So if I'm going to plug it into my formula, well, let's look at the formula. Area equals base times height. So what do we have? We have the area, so go ahead and plug that in. 120 millimeters squared equals the base, 24 millimeters, times the height, x. So to solve this for x now, that's my height. I want to find that. I need to divide each side by the 24 millimeters. Those cancel out on the right side, so I'm left with x equals 120 divided by 24 gives me 5 millimeters. So the missing height here, the height of this parallelogram, would be 5 millimeters. This next example, I'm given two altitudes in a couple different bases. So I'd say this AD is a base of the parallelogram because I have an altitude that goes to it. I also have that CD is a base because BF, an altitude, goes to it. So I have two bases and two altitudes, two heights in this figure. Let's write up here the area of a parallelogram real quick. Area equals base times height. If I want to find the area first, or let's find the area first, because without it I cannot find this missing height. I'm only looking for x here, which is the length of BE. So let's start with the area of the whole parallelogram. So area of the whole parallelogram, I have to use this 20 and this 10 because those are they go together. The base and the height go together. Here's my base, here's my height. I can't use this height and this base because I don't know what x is yet. So my area of the whole parallelogram equals the base, 10 feet, times the height, 20 feet. 10 times 20 is 200, so the area of this parallelogram is 200 feet squared. Now keeping this in mind, now we're relating this back to a very similar example, or a similar problem to the previous example. The area of this parallelogram is not changing, so I need to use this 200 feet squared in order to find my second altitude. So let's plug it once again into our formula, area equals base times height. This time I'm going to use my area of 200 feet, 200 feet squared, equals the base, 25 feet, times my height, x. Again, I'm looking for x, I'm looking for the length of segment BE here. So to get rid of this, get x by itself, I need to get rid of the 25 feet. So divide by 25 feet. Those cancel. Divide the left by 25 feet. 200 divided by 25, I'm going to be left with x equals 8 feet. So if you're given multiple altitudes, multiple heights in one parallelogram, sometimes you do need to find the area of the whole parallelogram first before you can go back and find the missing altitude. Moving forward, we're going to get into our second objective, is proving different things are parallelograms. So here's my given statement in this first proof. Given that WXYZ is a parallelogram, so WXYZ, there's my parallelogram. We're also given that MZ is perpendicular to segment WN. Here's segment MZ perpendicular to segment WN. Also given that segment NY is perpendicular to segment WN. So let's start with what we know. We know what we're given. Parallelogram WXYZ. We're also given that segment MZ is perpendicular to segment WN, and given that segment NY is also perpendicular to WN. We know that because it is given to us as our given statement. Good. I'm trying to prove that MNYZ is a parallelogram. In order to prove something in a parallelogram, we need to prove the opposite sides are parallel. So let's look at what our given information is. We already have WXYZ. WXYZ is a parallelogram. If this is a parallelogram, I must know that my top, WX, or in our case, WN, is going to be parallel to ZY. Because it's a parallelogram, I can add that to my statement. WN, segment WN, is parallel to segment ZY. And what that is just the definition of a parallelogram. The definition of a parallelogram says a quadrilateral with two pairs of opposite sides that are parallel. If I've proved that the top is parallel to the bottom, the next thing I need to do, again, is to prove MZ parallel to NY somehow. So let's go back to what we know in our given. We have MZ is perpendicular to WN, forms a right angle. We have segment NY is perpendicular to WN as well. If you remember back to chapter 2, I know it was a long time ago, but back to first semester, we had a theorem that said if two lines are perpendicular to the same line, then they are parallel. MZ is perpendicular to WN. Segment NY is perpendicular to WN. So that tells me that I can prove that segment MZ is parallel to segment NY. And just as that theorem that I just stated, if two lines are perpendicular to the same line, then they are parallel. Good, so I can go ahead and mark that up here now. So now I have the top and the bottom are parallel. I have the left and the right are parallel. One pair, two pairs. That allows me to prove that quadrilateral MNYZ is a parallelogram. And my reason is the statement that the definition and the kind of the theorem that we said earlier. If both pairs of opposite sides in a quadrilateral are parallel, a lot of abbreviating here, then it's a parallelogram. That concludes this lesson on proving things parallelograms and finding the area of parallelograms.